We just talked about reaction rates, and so we want to talk about two ways of changing the reaction rate. So the first way is, you can see from the drawing that we have a substrate here, we have a molecule here, and that it has to overcome all of this energy barrier in order to be able to come down and become a product. And so what you actually have here, this line right here represents the average energy that the reaction contain, that the molecules, the reactants contain at a given time. And so since it's average, we know that all molecules have have energy and that they can transfer energy to one another. We know that some of the molecules, very few, have energies down here, and then as you get up closer to this average, the molecules, more and more of them have energies right here. And then as you keep going up, there's a few molecules that have enough energy to reach that reaction. But the average energy is right here. And so what this energy right here that's needed, it's known as the delta G transition state, the free energy of the transition state, or the free energy of activation. This is the amount of energy that has to be overcome by the average energy molecule in order to have a reaction. And now, so we know that some of the molecules have enough energy, and actually more of them could end up having enough energy. So what happens is the energy contained in these molecules, oftentimes it's related to their temperature or their random kinetic movement. Some of them are moving really slow, and others are moving a little bit faster. And whenever, so for example, if I had one moving really fast and then one down here moving really slow, if two of these molecules simultaneously collided into that one, it would cause it to increase even faster, and it would bump it up into the a higher energy state, but it would bring those other two down to a lower energy state. And so the average energy is right here. So molecules can change the energy they have, but the average is going to be right here. And the highest, we don't know what the highest is, but we know that a certain percentage, if any reaction is taking place, a certain percentage of molecules have enough energy to react. Now, once they get this energy to react, they could statistically either stay on this side of the reaction, or they could go to this side of the reaction, but they have a higher probability of going to products if the reaction is spontaneous. And so we know that the reaction rate is directly proportional to the number of molecules that have reached the activation energy, or the delta G of the transition state. And so there's actually an equation that relates the reaction rate, the rate constant K, to delta G, and that's the Arrhenius equation, which is AE to the negative delta G transition state divided by RT. Now, just in case it isn't obvious from my horrible writing, this is all an exponent of E, so E to the delta G over RT. So we said there are two ways of changing this energy barrier right here. So what are those two ways? The first thing we could do is we could increase the heat. We see that temperature right here, this is RT, T means temperature in Kelvin. The temperature is directly related to the reaction rate constant. And so if we increase the temperature up to here, the average energy of the molecules was much higher, then it would have a much lower energy barrier, and delta G would be much smaller, delta G transition state. Unfortunately, in biological systems, we don't have the luxury of changing the temperature, and so there's one other thing in this equation that is variable, and that is delta G of the transition state. So if we could alter delta G of the transition state to make it right here, then we would also have a much lower energy barrier, and the average number of molecules that would be able to reach that barrier would be higher. Now, before I go on, I want to do a little bit of math manipulation to this equation. So we have that K is equal to A. A is a constant for each reaction. So A is not a molecule, it's not a substrate, it's nothing except for some constant for each type of reaction. E, of course, is 2.7 something, goes on and on forever, defined by a very specific formula. And then negative of delta G transition state over the gas law constant times T. Now we could rewrite this to, we can take the inverse. 1 over K is equal to 1 over A times 1 over E to the negative delta G transition state over RT. Now, anytime you have a negative exponent and it's under a fraction, so what that actually means, and I'll go ahead and give you a numeric example. If I had 10 to the negative 1, that's actually equal to 1 over 10. If I have 10 to the negative 2, that's actually equal to 1 over 10 squared. And then inversely, if I had 1 over 10 to the negative 2, that would be equal to 10 squared. And so there's actually a very simple mathematical proof for this, but this is also something you should have learned in a pre-algebra class, or maybe in your algebra class, which is basically properties of exponents. And so we're going to use that rule right here with e to the negative delta G transition state. So 1 over K is equal to 1 over A times e to the delta G transition state over RT. So what this shows us is that K is inversely proportional to E delta G RT. In other words, the larger that this number is that we get from this, the smaller K has to be. So if I have 1 over 1, that equals 1. But if I have 1 over 2, that's 1/2. So in order to make this larger, K has to be smaller. So I could say that K is 0.1, and that would actually make this term equal to 10. So the larger this term is, the smaller K has to be. So what that means is if I were to increase the temperature, that would make this numerator smaller. This fraction would be smaller, and I would actually increase the reaction rate because this term would be lower. So increasing temperature or decreasing delta G, either one of those will increase my reaction rate. And so that's what a catalyst does. A catalyst decreases the delta G of the transition state. And so and the way they do that is by transiently combining. So if this is my substrate and then this is my catalyst or my enzyme, the way they do that is by transiently bonding somehow to the substrate, whether that's a covalent bond that can be formed and broken, or whether that's a hydrogen bond or some kind of bond. They transiently combine with the substrate in order to bring about more favorable conditions. And so there's two principles that we have to keep in mind when we're talking about a catalyst. And so enzymes are biological catalysts. The first one is that they are regenerated, so they are regenerated, they're not used up, and they can continue to power more reactions. And number two is that they have no effect on the overall delta G, on the overall change of free energy. So I'm not talking about delta G of the transition state. I'm talking about the overall change of free energy. They do not change it at all. So if we go back to the reaction we talked about in a previous video, the reaction of B yielding P, we can actually graph the velocity of that reaction based on the concentration. So it makes a straight line like this. The velocity changes by adding more reactants, and the slope of that line, so the slope is equal to K. And that's a horrible K. Let me do that one more time. Now, if we add an enzyme catalyst, something happens. So the rate initially looks like it's going to follow a straight line, just like it did without catalyzed reaction. But as it gets higher and higher, it actually starts to slow down based on the concentration of B to the point that it levels off and follows a straight line. And the highest value that it can reach on the velocity, this is V max. This velocity is known as V max. This shows that the velocity is no longer dependent on the concentration, that the velocity is independent, which makes it, once it hits V max right here, this makes it a zeroth order kinetics. Zeroth order kinetics. So the rate at that point is independent of the substrate concentration. And the reason that this happens is because you have so many enzymes. Let's say that this is my enzyme. And we have so many of those, and once you have all of those filled up, all the active sites filled up with substrate, and no more substrate can get in there to react, that point it's going as fast as it can possibly go. And so that's called the substrate saturation. And so that actually sets us up to start talking about the Michaelis-Menten equations and all of the reasoning behind those. So that's where I'm going to stop this video. Next one, we're actually going to go into the Michaelis-Menten enzyme kinetics.